And Benton will be looking at characterizing char rate and extent in fiber reinforced plastics using X-ray computed tomography. Benton is a UT Austin graduate where he received his BS, MS, and PhD in aerospace engineering, studying high-speed fluid dynamics and reentry aerothermodynamics. He currently works as a contractor for the Orbital Debris Program Office at Johnson Space Center, where he supports reentry safety and continuing improvement of the office's modeling tools. So Benton, it looks like you have your slides up, and it is all yours.
Thank you. Can everybody hear me?
Yes, we can hear you.
Excellent. So I thank you for the introduction. Today I'll be talking about some work that we did characterizing char in fiber reinforced plastics using X-ray CT scans in order to validate a new material charring model that we're adding to our spacecraft reentry demise model. So we'll start with a little bit of background and motivation on orbital debris reentry. Sometimes when a spacecraft comes in on an uncontrolled or even a targeted reentry, bits of the spacecraft may survive to the ground and pose a casualty risk to the general public. At NASA, we use the Object Reentry Survival Analysis Tool, or ORSAT, and it models the spacecraft as a collection of nested components, and each component absorbs some amount of aerothermal heating along its trajectory, and when it absorbs enough thermal energy to completely melt or vaporize the material that comprises the component, we consider that component demised, and any child objects are then released onto their own independent trajectories. For traditional aerospace materials like titanium or aluminum, this melting or vaporization model works really well. However, for things like carbon fiber and glass fiber and Kevlar materials, this model does not necessarily work as well. The polymer matrix that holds the fibers together can char, and in many cases that char can be structural and can continue to hold the fibers together well past what we might consider the failure temperature of the material. And it is unclear whether the aerodynamic shear is enough to shred the fibers after the matrix has been charred. And so the ODPO did a series of test campaigns, or the Orbital Debris Program Office did a series of test campaigns to measure the charring and strength of different composite materials in a simulated reentry flow. We did our measurements at the University of Texas at Austin inductively coupled plasma torch. And our objectives with the test were to measure the charring and char rate and the effects of heat flux and surface temperature and surface oxidation on the char rate in the material, and then measure the bend strength of the sample during and after heating. I will focus on the first four objectives for this talk. So our test matrix consisted of three different types of fiber reinforced plastic. Used a standard G10 glass fiber reinforced epoxy, which you might find in circuit boards most commonly, and a carbon fiber reinforced epoxy, and a carbon fiber reinforced phenolic resin. We used both an oxidative and a non-oxidative condition, where the oxidative condition had a mixture of 2% air and balanced argon. And this low air mixture was meant to approximate the oxidation conditions of high altitude, even though the facility itself is at atmospheric pressure. And then we tested 2 different heat fluxes and exposure times from 5 to 80 seconds to cover the full range of expected heat pulse times for a low Earth orbit reentry. For various reasons, including ease of test sample changeout and performing 4-point bend measurements on the samples during test, we used a rectangular test sample, and this caused the charring and the heat flux to be very three-dimensional, both on the surface and inside the sample, and this made estimating the char depth from the mass loss of the sample very difficult. So we needed a direct measure of char depth. One of the options was to cut cross sections of the samples and measure the char thickness under a microscope, but we chose to do a non-destructive measurement. We X-ray CT scanned the samples and then used MATLAB's 3D image processing to measure the size of the different density regions inside. So I'll go through quickly what that looks like. So we have three different examples of our test samples here. We have the carbon fiber epoxy, carbon fiber phenolic, and glass fiber epoxy. And all of these were exposed to the plasma for 40 seconds. We first take the CT scan of these samples, and you can see a cross-section through the middle of the sample crossways in these images, and you can see the difference in X-ray transmissivity between the charred material and the virgin material. And then we were able to use this difference in exposure to run a boundary surface algorithm to measure the outer surface and volume of both the virgin material, which is colored in red in these plots, and the char material, which is colored in gray. And then from those surfaces, we can then generate a heat map of the char depth in the sample. And so we put all that together, we can see that we can get a good measure of the char depth over time in each of the different types of samples for each of the different conditions. We have only scanned about a third of our test samples so far, but you can already see that there are slight differences in the char rate between the glass fiber and carbon fiber samples, but the largest difference in char rate is obviously the incident heat flux on the sample. And the difference between oxidative and non-oxidative is really within the error bars of our measurement. So we can look at just the char front velocity for each of these materials and conditions. So the glass fiber epoxy chars about 18% slower than the carbon fiber epoxy, and the carbon fiber phenolic chars about 28% slower than the carbon fiber epoxy. We can also get the overall increase in volume of the whole sample over time. The carbon fiber samples increased in volume a little bit, up to about 35%, I know it says under 30% on there. That's a typo. And this is almost all due to fabric layer delamination, though that initial spike at the beginning at 5 seconds is due to soot accumulation on the surface and would probably not be seen in a real reentry with full high-speed flow. And then you can see that the increase in volume levels off for the glass fiber. And this is because as the layers delaminate, they start to melt very quickly and then are blown away even by the fairly low speed flow in the plasma torch. So we use this data to validate our new material charring model in ORSAT. And this has been more completely described in previous presentations, but our basic model assumptions are that the char formation can be modeled by setting the material density equal to a function of peak temperature. So basically, the density is, we just take the thermogravimetric analysis of the mass loss at specific temperatures and translate that into a density versus peak temperature for the material. And this allows us to generate custom models for any kind of proprietary CFRP or any kind of FRP material that the spacecraft may be using. And it also allows very fast calculations, which are important for ORSAT. We also assume there is no volumetric expansion. So you saw in one of the previous slides that this is not strictly speaking true, but it is a limitation of how ORSAT meshes the components. And the other material properties are not functions of peak temperature, they're only functions of current temperature. And this is a limitation of how ORSAT calculates thermal properties. And this is not necessarily true, but for ORSAT, once a component begins cooling, its thermal properties no longer have any effect on its ultimate contribution to casualty risk. And so we don't care what the thermal properties are after the sample has been heated to its peak temperature. And then we can also calculate the heat released and or absorbed by the pyrolysis process as a volumetric source term. We generated 2 new built-in models for the ORSAT charring model. We have a built-in generic glass fiber epoxy model and a built-in generic carbon fiber epoxy model. And these use the density versus peak temperature functions shown here. And so we then want to use the test data from the plasma torch to validate our model in ORSAT. So we ran an ORSAT run that was designed to mimic the plasma torch test as closely as possible. We used our non-tumbling box shape primitive model with 50 thermal mesh nodes, and this is a 1D thermal mesh from the front surface to the backside surface, and defined a user-defined trajectory that kept the heat flux between 21 and 23 watts per square centimeter for the full 80-second simulated flight time. And the model fragment was 25 by 80 by 10 millimeters to match the dimensions of the test coupons. And then 2 separate runs performed, one with the charring CFRP material and one with charring GFRP material. So you can see the results of the model versus the test data here. And you can see that there is a slight overprediction of the CFRP char depth, and it's relatively constant between 40 and 80 seconds. And this is probably because the heat flux in the plasma torch test case was localized to the center of the sample and not spread over the entire top surface of the sample as in the as in the ORSAT simulation. There is an even larger overprediction of the glass fiber reinforced char depth. And this is likely because as in supersonic flow, the molten glass will be removed very promptly. And in the plasma torch test, the molten glass was blown away only after it had completely liquefied. So we had a little bit more of a thermal protection layer of the molten glass. So these are some comparisons of the stagnation temperature between the model and the tests. In both cases, the model predicts a temperature about a couple hundred degrees Kelvin too low, and we're not sure if this is a problem with our emissivity assumptions or if or our material properties. The backside temperature matches a little bit better, but does not, but overpredicts the final backside temperature, and could indicate that our thermal conductivity is a little bit too high. So conclusions, we were able to successfully use X-ray CT scanning to measure the full 3D extent of char and virgin material within the sample, and then used that to validate our new ORSAT 7.0 charring material model for fiber reinforced polymer composites, and found that the charring model compares favorably with these char depth measurements from CT scans. And with that, I will open the floor to any questions.
Great, thank you, Benton. If anybody has any questions, that would be a great time to place them in chat. Somebody put the non-tumbling block, ... Was this a separate conduction model?
I'm not sure what you mean. So ORSAT provides multiple different, basically primitive shapes that you can model components as, and you can have cylinders and spheres and boxes and flat plates, and many of these can be modeled with various. Since it's a 3 degree of freedom model, we model the drag and heating for tumbling items with just tumbling models rather than a 6 degree of freedom calculation. And the non-tumbling block essentially just faces one side of the block toward the stagnation point, and then calculates the thermal conductivity or the thermal load through the thickness of the sample.